Good evening, everyone. Let's wait until 8:05.
Good evening, doctor. Just a quick question. Any idea when we will get the result for the assessment number one?
The marking is still in progress, so it will be finished this week. So you will get the mark will be released early next week.
Okay.
Good evening, Dr. Zheng.
Yeah,
Hello?
yeah. Can you hear me?
Okay, thank you. I just check my assignment one today, and I did not see anything yet because I remember you mentioned the assignment will be marked today.
Yeah. The mark will be released early next week. There are many like submission and extension, so the release date is postponed due to that.
Okay, so will be early next week.
Yeah.
Okay, thank you.
So have you all got the email from uni about the exam time? So
Yeah.
the format of the final exam should be closed book. So the exam should be unsupervised closed book exam.
I heard you said unsupervised or supervised?
Unsupervised.
Unsupervised closed book.
Yes.
Right, okay.
So like how do you police that? Is there going to be record? Or do you have to have a webcam or anything like that?
Um, I'm not sure. I think that they just changed the system in this semester. Um, is there any instructions in the email you received? I think you will log in through the LMS. I will double check with the course coordinator to see which link you're going to use to get into the final exam.
Is it also true that the second assessment or assignment is due after the final exam?
Yes, the due of assessment two should be at the end of week 7,
Okay.
and the exam should be on Tuesday of week 7, right?
Okay, no problem. Thank you.
Was this an email that was sent for the assessment being unsupervised online sort of thing? Because I never got an email.
So you didn't receive the email? Um,
No, I have not received the email.
uh, Let me see.
I received the email, but the email said it's open book.
It should be
Yes,
closed book.
yes. With the unsupervised, it was open book last semester, and the email said that too.
Yeah. The email said unsupervised open book in my email.
Yeah.
Who received closed book one? I would like to know because I received open book one.
Can you forward the email to me
Yeah,
if you don't mind?
I looked at the email. It says supervised exam.
Okay, I go to find it and forward you.
I actually got an email as well that said it was an open book. Yeah.
I don't know. It is near.
From what I know, it only says unsupervised, but it is closed book.
Is it an issue if I didn't get any email?
Read the online instructions.
I received the email on the 7th of August. It says it's
It's in
time
the
for
chat,
your
guys. I'll just
for
put it in
your
the chat.
yeah, my email says it's time for your unsupervised online exam. But it doesn't say whether it's open book or closed book. It just says it's unsupervised online exam.
To be fair, it's probably better if it's closed book because they always make the questions harder on an open book exam.
Exam timetable.
That's my copy and paste format. You can see unsupervised open book assessments. That's from the information I received.
It doesn't say, it just says it is near time for your unsupervised
click the
online
link.
exam.
You click link, you go inside, and something jump out. You read that. That will be a PDF jump out.
On the online exam instruction, that link there.
Yeah. That.
Yeah.
If you click on the online exam instruction, it said supervised exam.
It said supervised open book
Yeah, it said
assessment.
semester 1 and term 3 online exam. This is not semester 1, no? If you click on this, you get supervised online exam, semester 1, term 3 online exam, important information.
Yeah. It says
there's no other instructions for this term though. So
I
we'll
draw
take
your
the latest
attention to the
information.
fact, gentlemen and ladies, that we are in term 4.
Yeah, but there's no other instructions, right? So you base
that's
it off the
only
last.
one, only instruction.
So surely from the university, someone can confirm. What is the normal process of confirming these type of things?
Okay. From what I know, it is unsupervised but closed book, and you may need to get into the exam link through the LMS. And yeah, I think currently the exam link is hidden, so yeah, you should not be able to see that right now.
So sorry, this is only my second course. Where the question might be, what is the difference between supervised and unsupervised exam?
Supervised is there's a invigilator just monitoring your entire session, and unsupervised there's no such real person sitting with you.
I mean, we are all, online anyway, isn't it? I mean,
So when they supervise and you're online, they can see your screen, and then usually they can see through your camera on you, and you have to do a room search to see that you don't have any notes or anything hiding that you would cheat or anything like that, or a second computer next to you or anything like that. Yeah.
Yeah. Previously, you need to attend like half an hour earlier to finish those investigation setup, whatever stuff. Yeah.
So unsupervised, you don't have to do that, no?
For unsupervised, you should not need to do that.
Okay.
Okay, let's get into our weekly contents. So in last week, we have talked about the deep neural networks. We talk about the neurons, the edge, the architecture of the deep neural networks. We talk about forward pass and backward propagation, those kind of stuff. But that's the basic structure or building blocks for the neural networks. In this week, we're going to talk about the convolutional neural network. And this type of neural networks are designed specifically for dealing with image tasks. So if the input is image, so we'd better use these convolutional neural networks to deal with that, no matter if it is like regression problem or classification problem, but we need to use convolutional neural network to deal with image, and it has better performance than the basic neural networks with pure neurons and edges. And before we talk about the actual convolutional layers in the convolutional neural network, there are some process we need to get familiar with beforehand. So the first one is inner product. So we have seen this inner product calculation before, like the linear regression. So for inner product between two column vectors. So this notation is representing the calculation of inner product. So it is equivalent to the transpose of vector A multiply the column vector B. So it is equivalent to the element-wise multiplication between these two vector and sum the products together. And this will be the result for this case. So for inner product on two vector, it is a linear combination between the elements in this two vector. So that's the inner product. And we can also apply inner product on two metrics. So that is for 2D cases. And for inner product on two metrics, we're doing similar stuff. So we multiply each corresponding elements in the two metrics, and we sum all this product together, and that will be the result. So basically what it's doing is, for this example, it is calculating 1 multiply 5 plus 2 multiply 6 plus 3 multiply 7, 4 multiply 8, and the sum will be 70. So this is the inner product for two metrics, and this is also the operation we will perform in the convolutional layer we will talk about later. And this inner product on two metrics is also equivalent to the inner product of two flattened vector. So we can see that if we flatten this matrix A and B, so this would be equivalent to column vector 1, 2, 3, 4, and the vectorized matrix B would be 5, 6, 7, 8. And if we calculate the inner product between these two vectors, we are kind of just multiply the corresponding elements together and sum them up. So these two are equivalent. So that's inner product for two metrics. And we can also do inner product on higher dimensional array. So let's say for we may need to do the inner product for, let's say, two 3D arrays. And the operation is very similar. So we simply just multiply the corresponding elements together and then sum all these product together. So that will be the inner product for higher dimensional array. And it is also equivalent to the vectorized version for the higher dimensional array. So it is equivalent to flatten the high dimensional array into vectors and calculate the inner product of two vectors. Okay. Any questions regarding the inner product? Okay, good. So then we will talk about the convolution. So that is the core operation in this CNN neural networks. So for this CNN convolutional neural networks, it is mainly used to deal with image. So let's look at the data first. So for the input, so we should be given some input images, and each is represented by, let's say, X, and J is just the index for the input. And each input image should come with a size. So that would be the width and height of the image. So that means if the image come with size 28 by 28, that means there are 28 pixels on the rows and 28 pixels on the columns. So that means there should be 28 such cells on the columns and 28 such cells on the rows. So in last week, if we talk about how to dealing with such image as input. So in last week, we need to vectorize or flatten this input matrix into a one-dimensional vector. So in last week, if we are going to use pure neural networks like pure neurons and edges, we need to flatten this matrix into a 784 dimension vector. So that is a vector with 784 entries in the vector. But now, if we are going to use CNN to deal with such input, we don't need to do such conversion. We don't need to flatten the 2D matrix into the column vector. And what is the convolutional operation? The convolution operation requires two input. So one is the input image. So for 2D image, it is just a 2D matrix. So it comes with a size specifying the number of rows and columns, or specifying the width and height of the input image. So 5 by 5 means it must have 5 rows and 5 columns. So in total, there are 25 pixels in this matrix. So this is the first input for the convolution. Another input for the convolution operation is the kernel, or called filter. So these two terms are used interchangeably. It also comes with a size 3 by 3. So it is a matrix. It is a 2D matrix and come with the size 3 by 3. So basically, in summary, the convolution requires two types of input, and both of them are matrix. And one is representing the input image matrix, and another input is the kernel or filter matrix. And what the convolution operation do is it is trying to place the filter onto the image input image at different locations. So it's trying to overlay this 3 by 3 matrix onto this 5 by 5 area. So it can be placed here at the top left corner, or it can be placed at the middle of the bottom. And it can also be placed like here to be overlaid onto the input image. So now let's think about this question. So how many 3x3 patches. So this patches is just representing a sub area in the input image that has same size as the filter of kernel. So it is representing the overlaid position of the kernel. So how many 3x3 patches does a 5x5 image have? So how many candidate positions that this kernel can be placed on the input image? So would be the answer. So there are in total 9 locations that we can place the kernel on the input image. So if we think about the positions in horizontal direction, so we can place it at the top left corner or here in the middle or on the top right corner. So in horizontal direction, there are 3 possibilities, right? That we can place the kernel. And if we think about the direction vertically, so we can place it at the top left corner or the middle of the left-hand side of the input image, or we can place it at the bottom left corner. So there are only 3 possible locations along the vertical direction. So and combine these possibilities on these 2 directions, we will get 3x3 possible locations, and that is equals to 9. How can we calculate this 3? We can follow in this equation. So 5 is the image size, and 3 is the kernel size, and plus 1. That is the 5x3, 5 minus 3, 2 plus, and that is 3, and this is also 3. So each parenthesis is representing the possibilities along one direction.
Excuse me, doctor. What is the number 1 coming from? Because I do understand that 5 is from the 5 pixels for the input image. 3 is from the kernel, but number 1, where is coming from?
Okay, so let's think about it in this way. So in total, we have, let's say we have 5 pixels, 5 locations along the row, right? And let's just ignore the first 3. Let's ignore the first location, that is 3. So that is 5 minus 3. So left 2 possible locations left. We are sure that this kernel can be placed at these 2 locations, right? If we just sliding this kernel along the horizontal direction. So this 5 minus 2 is representing these 2 locations. And the 1 is the initial location we just ignore. So this is just one interpretation for this 5 minus 3 plus 1. And you can have your own interpretation, but this is just equation calculating like how many possible locations that we can place the kernel onto the input image. Okay.
Okay, so always will be 1 or just depends of the.
It should be always 1.
Okay.
Yeah, if you just try different
Will be a
values for the input image, let's say 6x6, and we should have like one more column and one more row. And now 6x3, 6 minus 3 will representing these 3 locations, and plus 1, that is the initial locations, right? So
Okay.
there are in total 4x4.
Okay, got it. Thank you.
16 possible locations. Okay, So when we place the kernel at different location on the input image, we need to do some process. We need to calculate the inner product. We will talk about that later. And then that means we will have a generated value for each possible location. And in this case, since there are in total 9 locations, we will get 9 inner product result. And how can we organize this result? So we would like to use a matrix to represent this 9 inner product result for different overlaid position. So we want to use 3 rows and 3 columns to represent and also represent the corresponding overlaid position. So we can see that after the convolution, the result should be another matrix, and the size is 3 by 3, representing or holding all the calculated value at different overlaid position. So let's say if we place the kernel on the top left corner, and let's say we do the inner product for these 2 matrices, and the result must be one single value, and this single value will be placed here at the top left value for the result matrix. And if we place the kernel at the center of the input image, then the inner product of the patch and the image patch and the filter would be another value. And we will use the center value of the result matrix to hold the inner product value. So we are organizing this inner product result in this 3 by 3 matrix. It's not only holding those inner product result, it also maintain the correspondence between the result and the overlaid position. Let's look at an example. So if we overlay the kernel to the top left corner, so we are going to calculate the inner product of the patch and the filter. So how can we calculate the inner product? We are calculating the element-wise multiplication, and we sum all this product together. And the result must be 4. So that would be, let's say, 1 by 1, 1, 0, 1 by 1, 0 by 0, 1 by 1.
In this binary case, we're actually ANDing them.
Wait a second, let me finish. So there should be, this is 1, 0, this is 1, 1, 1. So the inner product between these two, this image patch, that is the sub area overlaid by the kernel, and the filter, that is the kernel matrix. So the inner product of these 2 matrices will be 4, and this 4 will be placed in the corresponding location of the in the convolution result. Sorry, what was the question?
It's all right. I figured it out. I made a mistake. My apologies.
Okay, that's all right. Okay, now we have finished the first overlaid position, and what if we then slide the kernel to the next position? That should be the second position in the first row. So then we will get a different image patch, right? And the kernel value should stay the same. So we are using different image patch and inner product with the filter matrix. And the inner product result would be 3, and 3 would be entered in the second cell of the first row in the convolution result matrix. and we can keep sliding this overlaid position and calculate the inner product of the image patch with the filter matrix, and then enter the inner product result to the corresponding entries in the convolution matrix. So we keep sliding the kernel until the last position. That will be the bottom right location, right? And we calculate the inner product, and the value is 4. So we entered into the last entry of the convolution matrix. So this would be the entire process of convolution operation. Let's look at another example. So here, what if we have a input image of different size? So previously the image comes with 5 by 5, and now the image is 4 by 4, and we still use the 3 by 3 kernel. And now, how many possible locations would we have? Or how many possible locations that we can place the kernel? So along the horizontal direction, we should have, this is one candidate, this is the second candidate, and that's it. So we have 2 along the horizontal direction. And for vertically, we have 1 candidate, and this must be the second candidate. So we have 2 candidates along the vertical direction. So in total, we should have a matrix that can hold this in total 4 convolution inner product result. So we can see that the result comes with size 2 by 2. And how can we calculate this size mathematically? So we can use the input image size minus the filter size plus 1. And we do the same for the other direction. So this must be 2, and this must be 2. So 2 by 2, that is the expected convolution result matrix size. And here is the equation for that. So we have input come with size D1 and D2, and we have filter size K1 and K2. And the output convolution, the output of convolution is a matrix of size D1 minus K1 plus 1 multiply D2 minus K2 plus 1. So that is how we calculate the expected convolutional result matrix size. Is that okay?
Yeah, just a quick question regarding the filter dimensions. What stops you from choosing a filter that is
Sorry?
What stops you from choosing a filter's dimensions which are bigger than the image itself?
You mean the size of the kernel?
Yes, the size of the kernel to become bigger. Then, I mean, is there like a constraint or a logical reason?
Okay, normally we choose odd number like 1, 3, 5, 7, and so on. Because with this odd number, odd size, it has meaningful value at the center of the kernel. So if we sliding the filter over the input image, we can just imagine that we are kind of scanning over the input image and place the inner product result to the center of the overlaid image patch. So that's kind of convention. So we would prefer odd number for that. And of course, you can use even number for the filter size. And another thing is the size of the kernel would be related to something another term called receptive field. So basically, it will affect how much information you will consider when calculating the feature. So later on, we will talk about after a few slides. So we will talk about that this convolution operation or convolutional layer will serve as kind of feature extracting or process, or sometimes we treat this convolutional layer as feature extractor.
Perfect.
So different size will change what kind of feature you are going to be extracted. So with smaller kernel size, that means the extracted feature will focus more on the local patterns, like local change, kind of like edge information, local maximum, such kind of local pattern. And if you use large kernel size, it will extract more contextual information or contextual feature from the input image. So that's the difference.
Thank
So
you.
yes, you need to it is also a consideration that we need to think about when we build the convolute CNN layers. But normally we can always start with smaller kernel size, like 3. It is recommended.
Sorry, Dr. Zen. I think he was asking, what if we choose the bigger filter than the bigger size of the filter
Then
than
the
the
input
input
image.
image? Yeah.
Normally we don't do that because this is a very small image. Like normally the image would be let's say for an image that we took from the, let's say, iPhone or whatever mobile phone, the size would be large, like over 1,000, something like that. So you won't meet such small input image. And normally the kernel size is, I think, is no bigger than 7. Normally we don't use extreme large filter. So normally we don't set filter that has larger size than the input image. And if you use the large kernel size, it kind of not extracting any local information. It is just replacing the entire image with a single value. So let's say for this one, if we have a 5x5 kernel applied on a 5x5 image, the result would be just a single value. So it kind of using one value to represent the whole image. So it is kind of a global feature describing using one global feature value to describe the entire image. So it may be not useful for some image-based problems. Okay.
So I've just got one question. If you have the convolution results and the kernel, can you always go back to the exact input image, like go backwards, or is that not always the case?
Okay, you want to do the inverse operation. Let's given the result and the kernel. Can we recover the input image? Not really. Not really.
Okay. Thank you.
Okay. Later on, you will know that this kernel will be the parameter.
Doctor, excuse me.
Let me finish this one. So later on, you will know that this kernel will be the weight matrix holding all the trainable parameters that we need to tune or learn during the training phases. So this should be so all the trainable parameters are contained in this kernel. Okay. What's the question?
Sorry, it's just this 3 by 3 multiplied by 3 by 3. This is not vector multiplication, isn't it? Like, rather we use that formula on the third slide. Is that correct? Because 3 by 3 vector multiplied by 3 by 3 is another 3 by 3 vector.
It is doing the inner product between two matrices. So it is doing the element-wise multiplication, but it need to sum all the product together. So like this one. So the result must be one single value.
Yeah. Okay.
Okay. So now this is convolutional operation performed on a 2D input image. So what if we are going to apply the convolution on a 3D input? So maybe the input data is not grayscale image. It may be a color image. So color image come with 3 channels representing RGB, right? So red channel, green channel, and blue channel. So the input is not a 2D matrix anymore. It is a 3D tensor. So if it is let's say for this image, if it is color, then the size of the input would be 28 by 28. That would be the, let's say, width, height, and this would be the channel. The 3 is representing the channel number. So now, if this input image is color image, we will have a third dimension representing the 3 channels. So how can we do the convolution over this 3D data? So we are doing similar stuff, but size of the tensor will be a little bit different. So actually, this is still 2D convolution. So although it is applied on the 3D input, it is still 2D convolution. So why it is 2D convolution? Because this the kernel is going to be is sliding through the input data only along the 2D plane. So that's why it is called 2D convolution. Similar for this one, the kernel is placed on the input image and sliding over the entire image, but all this sliding process is performed on the 2D plane. Similarly, even though this this kernel is placed on the 3D input data, the sliding direction is always on this 2D plane instead of sliding along the third depth direction. So there's no such sliding here. So it is still 2D convolution. So to apply this 2D convolution on the 3D input, the size of the tensor or the filter must be different from the version applied on 2D input data. So we need to extend this third dimension of the tensor to match with the depth of the input data. So the input data has 3 channels represented by the depth of the input array. So we need to specify size 3 for the third dimension or for the depth of the tensor. So now if we are specifying that we are going to use a 3x3 tensor to do the convolution on this color image input data, we are implying that we are going to use a kernel of size 3x3 for the width and height, but for the depth of the kernel, it is matching with the depth of the input, that is 3. And then we are going to slide this 3x3x3 cube tensor along the width and height of the input direction. And then at each location, we are going to calculate the inner product between the kernel 3D matrix and the image patch 3D matrix. So using this inner product operation. So again, we use the element-wise multiplication and sum all the product together. And the result must be just a single value. Let me get back. So at different location, so we will get a single value representing the inner product. And we just keep sliding the tensor, and we are going to and then calculate the inner product. We are going to filling up all the values in the result matrix. Because this kernel, it is 2D convolution, and the kernel is only sliding along the width and height direction. So the result must be a 2D matrix, no matter what's the number for the third dimension, no matter what the size of the depth of the input. We will always get a 2D output matrix for this 2D convolution. And the size of this output matrix should be D1 minus the kernel size is 3, so minus 3 plus 1 by D2 minus 3 plus 1. And this is just equals to D1 minus 2 and D2 minus 2, right? So that if we can follow the same equation as defined here, we can get the size of the output matrix. Okay, that would be applying 2D convolution on 3D input data, or say applying 2D convolution on color image data. Is that all right?
A quick question, just to make sure that I got it correctly. So in this case, the input dimensions are D1, D2 into 3, and our kernel size is 3 into 3 into 3.
Yes.
And the output is 1 into D1 minus 2, D2 minus 2.
Yes. So the input is 3D, it's the 3D tensor or 3D array, and the filter or kernel is also a 3D array, but the result of convolution is a 2D matrix, is in 2D.
This is the 2D convolution, because we have a convolution where we increase the
we have 3D convolution, but it is out of this scope. So, but for 3D convolution, you may imagine, let's say we have input data, maybe some medical image data that have many slices, and we stack them together, so we will have larger depth. Let's say now the input data will be D1, D2, let's say the depth is 6. And now we are using the same 3D filter, so 3 by 3 by 3. And now this filter can slide along the depth direction, right? We have possibility to place this 3D cube at locations along the depth direction. So that would be the 3D convolution, and the result would be a 3D array instead of 2D matrix.
Right. Gotcha. That part. How do you increase the number of output channels?
How to, you mean for 2D convolution, how to increase the...
But no, in the convolutional neural networks, we have seen that sometimes like input channels is 3, but we output 8 channels, 9 channels.
Yes, we can use multiple filters to do that. So for one filter, it will generate one 2D matrix. What if we are using, let's say, more filters to do the operation? We have, let's say we use 5 filters to do the operation. We will then have 5 different output metrics, and we stack these metrics together. We will get like output of 3D.
Yep.
Okay.
Thank you.
We will talk about that later when we talk about the layer. Okay. So now we are familiar with the operation, the underlying computation. Now let's say let's look at what kind of structures that we can use to build the convolutional neural networks. So there are 3 components. So one type of layers is convolutional layers, and another one is pooling layers, and then the fully connected layers. So the convolutional layers will be, for simplicity, it is just the layer that has the convolution operation, that performs the convolution operation. So that's why it's called convolutional layers. And we will talk about pooling layers later. It is used to reduce the parameter size. And the fully connected layers are just the pure or the dense layers we talked about in last week. So it is composed of neurons and edges. So that is called fully connected layers or dense layers. So let's look at them one by one. So for convolutional layers, it is a very effective design. So let's say think about this case. So if we use the pure neural networks structure, we need to flatten the input matrix. So in this case, it is a 28 by 28 image. We need to flatten it into vector that is holding 784 elements, and that would be the input. And we need 784 neurons in the input layer to hold each pixel value, right? And then to pass this value into the next layer, we need to connect each neuron in the input layer to the one neuron in the next layer. So that means we need 784 edges or parameters to do that. So whenever we add a new neuron in the next layer, we need to add another 784 edges. So we need an extra 784 parameters to learn or to tune for the model. But with this convolutional neural network, what we can do is we can just define a 3x3 kernel. And this kernel only hold 9 parameters. And these are all the parameters we need to tune. So to connect the input image to the next layer, no matter how large the input image is, we only need 9 parameters to connect the input with the next layer. So that's a benefit of convolutional layers or convolutional operations. So it's reduced the number of parameters dramatically. And why we use such kind of convolutional operation is we assume, like we believe that for this kind of image data, the pixels must have some correlation with its surroundings. So we don't treat each pixel as some independent features or values. There must be some inherent correlations among them, especially for pixels around nearby. So that's why we design this convolution operation to take into all these surrounding pixels into consideration to generate certain feature values. In this way, we kind of consider not only the single pixel in the image, we also consider all the small neighboring areas in these locations. And let's keep going on. So that's why I said the convolutional layer are more effective. So it reduces the parameter dramatically, and it also considers the neighboring features. So layers close to the input learns that will be learn low-level features. So let's look at I will show you a demo, and I think it may be more helpful for you to understand this process. So you can see the shared web page. So this is a demo for the convolution operation. So the input will be just handwritten digit. So this is 0, and we are kind of sliding this filter over the entire image space and to generate the convolution output matrix. So this filter now come with first row all -1 and second row all with +1, and the third row is all 0. So if the value in this filter is presented in this way, this filter may serve as edge extractor. So it is kind of extracting edge information from the original image. So this is useful to extract horizontal edge. So let's say if we just sliding this filter and do the convolution operation, you can see that we keep sliding this filter, and after we sliding over all the image area, we can see that all this background has 0 values, and for these locations, we can see the overlaid position on the left-hand side, right? It is highlighted. For this output with high values, that means these areas must holding some strong horizontal edge informations. So this filter with convolution operations can serve as feature extraction, and it is extracting the horizontal edge information. What if we change the pattern in this filter? Let's say we change it to left edge filter. Now the left column is all -1, and the middle column is all 1, and the right is all 0. And then if we do the same operation, we can see that this area is holding high value for the extracted feature information. So now this filter with this pattern can serve as a horizontal edge extractor. So that tells us that with different pattern or different value specified, different value patterns specified in this kernel filter, each filter can serve for different purpose, like used to extract different type of features. And Let me get back. So that explains this statement that we use this convolutional layer to learn low-level features. Like for example, extract the edge informations and to represent the lines in the image. And layers deeper in the model learn high order or more abstract features like shape and specific object. So we not only use just one layer, one convolutional layer, we are stacking multiple convolutional layers together. So the later layer can serve as a combination of previous low-level features. So you can imagine that if we combine the edge features and like horizontal edge and vertical edge features together, we somehow just manually or build some new features that can represent the specific shape or corners or something like that. So the layers deeper in the model can represent higher order or more abstract features. And there's a limitation of the feature map that they record the precise position of features in the input. A small movement in the position of an image in the input image will result in a different feature map. So that is because so for example, for this case, so what if we have the same handwritten image of 8, but now we are not placing the 8 in the middle of the image. We kind of place it at the like we shift it to the right. And now the extracted feature must be corresponding to the location of the input image, right? Maybe previously, if we draw some edge features from the image, we may get something like, let's say, horizontal edge here, some horizontal edge here and here. And now for this image with different or shifted locations for the digits, we may have shifted features corresponding to different locations for the handwritten digit. So this extracted feature is invariant, variant to the locations and rotations operations. So that is one limitation. So if the image is rotated, shifting, or there are any other minor changes to the input image, the corresponding feature map extracted will also change accordingly. Okay, so let's have a 5 minutes break. Let's come back at 9:09, and then we continue to look at how to build the model using this convolutional layer and how to calculate those parameter numbers. So let's come back at 9:09.
Hi, doctor. Just I missed out earlier at the beginning of the session. He just wants to confirm. So the exam's on the 25th and it's unsupervised. Is that correct?
Yeah, it is unsupervised online exam. It is closed book, unsupervised.
Yeah. And it's on the 25th, which is like a couple of days after the final week.
Yeah, it should be Tuesday of week 7.
Yes. Okay.
Yeah.
Oh, good. So that's gonna be earlier than the due date for assignment 2.
Yes, yes.
Okay. All right. Cool.
Doctor,
Thank you.
if it is unsupervised, how do you police? How do you know that somebody is opening the books or not? If it is unsupervised.
That's how it is controlled by the university. Yeah.
We are online, doctor.
Okay, let's get back to the content. So for a convolutional layer, it is composed of not only one filter or kernels, it is composed of multiple kernels. So let's say look at this structure. So we have a input image. It is just one grayscale image. So it is 2D matrix, come with size 28 by 28. And for each kernel we used in the convolution operation, we will generate one feature map. And the size of the feature map must be 24 by 24 by 1, right? That is the result for one kernel. What if we are using 10 kernel? Then we are going to get 10 such feature maps. And if we stack them together, and the entire output of this convolutional layer will be of size 24 by 24 by 10. And this 10 is corresponding to the number of filters we used in this layer. So 10 filters corresponding to 10 feature maps in the output. And how many parameters we are going to use in this convolutional layers? So since the input is a 2D matrix, so the depth must be 1, right? So the depth of this kernel must be 1. So for each kernel, we have 5 by 5 by 1 number of parameters. That will be 25 parameters. Since we are going to use 10 filters, these 10 filters must be different. So we have 25 multiply 10 filters. So in total, we'll have 250 number of parameters. So these are the number of parameters we need to tune or optimize in the back propagation. And these are the number of trainable parameters in this convolutional layer. Okay, so there are a few aspects you need to know that what is the size of the output, how to get the 24, and what is the size of the kernel, and how many total parameters in this convolutional layer. Okay. And just like the pure neural networks, we need to apply activation function after this convolution operations, because without the activation function, those convolution operations is just some linear operations, and the model will not have the capability to capture the nonlinear relationship between the input and the output. So we need activation function to introduce the nonlinearity to the model. So here we just use the ReLU function to apply it on the feature map. So recall that the ReLU function will not change any value, that is greater or equal to 0. And for all the negative value is just simply set it as 0. So this is the ReLU function. So this function will be applied on each entries in this output matrix or in this stacked feature maps. So each value, it will check if each value is greater than 0 or not. For all the negative value, it's just set it to 0. And so in summary, the convolutional layer is just the convolution operation and the activation function. Okay, so that's straightforward. So for convolutional layer.
Sorry, doctor, I think I missed something. Why did you get 24 by 24?
Because we are using the 5 by 5 kernel and input size is 28. So for each kernel, for each for convolution operation of one kernel, the feature map or the convolution result should come with size 28 minus 5 plus 1 by 28 minus 1 plus 1, right? So this is 24. This is 24. And that would be the size for one feature map. And we have 10 filters, so we should have 10 such kind of feature map. So if we stack them together, the output will be a 3-dimensional array. So the 3-dimensional array should come with size 24 by 24. That is one feature map, and we have 10. Okay?
Thank you.
So the next type of layer is pooling layer. So it is a common solution for downsampling. So we can see that after the convolutional layer, the size of the data has been reduced. Let's say for this example, from 28 to 24. And what if we want to keep reducing the size of the output until some kind of expectation? Let's say for binary classification, we may just want it to be shrink to one value. Then we may expect that we need to perform like 5 or 6 extra convolution operation on the data, because each operation will reduce the size by 4, right? So it will require a lot of expensive convolution calculation. So then just introducing this pooling layer is a fast way to do this downsampling. So it will reduce the size of the data dramatically. So this is where a lower resolution version of an input is created that still contains the important structural element. So we not only just want to reduce the size of the data or reduce the size of feature map, we also want to maintain some important information. So we need to use this pooling layer. And the pooling layer operates upon each feature map separately to create a new set of the same number of pooled feature maps. So if we look at the diagram, we see that we apply the pooling operation on the result of the output of convolutional layer, and this operation will performed on each slice of feature map, and it reduces all the feature map to the same size, and we can still stack them together. So that is what this statement is expressing. And pooling layer involves selecting a pooling operation, such as max pooling and average pooling, much like a filter to be applied to feature maps. So recall that we not only want the pooling layer to reduce the reduce the size of the data, we also want it to maintain the information, and we can choose either max pooling or average pooling to preserve the information. So for max pooling, it is basically preserve the strongest signal in the data, and for average pooling, it is kind of maintain the overall information in the input data. So these the considerations we need to think about during when we choose the type of pooling layers. So for max pooling, it is better used in some image classification task, because we want to highlight the importance of certain strong feature values like edge informations and so on, and we want to emphasize those existence of the feature and use those features to do the classification. So in that case, we would prefer max pooling. And for average pooling, that is, we want to maintain the overall or global information in the features. So in that case, we will choose average pooling. And the size of the pooling operation or filter is smaller than the size of the feature map. So we will see that. Specifically, it is almost always 2 by 2 pixels applied with a stride of 2 pixels. So that means we will talk about that when we explain the actual operations. So basically, it means the overlaid image patches on the input image will not overlap with other overlaid positions. And the pooling, this means that the pooling layer will always reduce the size of each feature map by a factor of 2. We will see that in the real operation. And the pooling operation is specified rather than learned. So there is no trainable parameter in these pooling operations. So it is just come with some fixed size. So if we specify the 2 by 2 as the size of pooling, so we will always reduce the input data to its half. So there are 2 common functions: average pooling and maximum pooling. We will see that. And the result of using a pooling layer and creating downsampled or pooled feature maps can be seen as a summarized version of the feature detected in the input. So let's look at the actual operations we're going to do in this pooling layer. So pooling reduces the dimensionality of each feature map. So the input of the pooling operation is just a single feature map in previous layer. And then we need to choose if we are going to do the max pooling or average pooling. Let's say let's do the max pooling in this case. And the pool size is 2 by 2. That means the overlaid. So we are kind of placing a window on the given feature map. And then based on the max pooling is going to calculate the maximum value for each patch of the feature map. So now this green area is the feature patch of the same size of the pool size. And it is going to calculate the maximum value in this green area. The maximum value is 100. So then we will output this 100 in the result matrix or result reduced feature map. And then come with the strat. Strat means how many pixels or locations it will jump over. So 2 by 2 means when we slide this window, it need to jump over 2 positions. So let's say it start from this location, and the next location will be here. So it is jump over the 2 locations in this green area. So if we're going to move vertically, so it still need to jump over 2 locations. So the next location in vertical direction would be here. So that is what strat means. So normally, this strat should come with the same size as the pool size because it doesn't want this Windows location to have any overlap with other candidate locations. But you can still, it is not compulsory. You can still set strat to be 1 by 1. So in that case, the next location will be here. And then the next candidate would be here. But normally we use the same strat size as the strat as the pool size. So let's say the strat is 2 by 2. Let's just erase everything. So we have done the pooling operations on the green area, and now the next location after strat 2 that will be here. Then it is going to calculate the maximum in this area. So the maximum should be 184, and the maximum value will be preserved and filled up and used to fill up the result matrix. And we then keep sliding this window and calculate the maximum value inside the window to fill up all the rest of the entries in the result matrix. So after this pooling operations, we can see that the input feature map come with size 4 by 4. And after we specify the pool size 2 by 2 with strat 2 by 2, we reduce this feature map to the size 2 by 2. So now it dramatically reduced the size of the data we need to process between layers. And also, with this max pooling, we kind of only care about the strongest response in this feature map. And we assume that this kind of operation can preserve the most important information in this feature map. And similarly, for average pooling, all the process would be the same. The difference is only how we calculate, like what value we are going to use to fill up the result matrix. For average pooling, instead of calculating the maximum value in the window, it is calculating the average value of these 4 locations. So it is just using different values to fill up the result matrix. So average pooling will consider more about the overall information in the area instead of the strongest signal in the feature map. We have seen that the pooling operations can reduce the dimensionality of feature map. So let's say for input feature map of size 24 by 24. So after we apply the max pooling with pooling size 2 by 2, this suggests that the stretch is also 2 by 2. So we reduced the size of the feature map to its half. So now it is 12 by 12 for each feature map. And because we have 10 such feature maps, so we should also have 10 feature maps with reduced size. So the output of the pooling output would be the size of the pooling output would be 12 by 12 by 10. So that would be the size of the pooling output. And unlike the convolutional layer, there's no trainable parameters. So this is just, you can treat it as some fixed operations just used to reduce the size of the feature map. And we can then apply or keep stacking more convolutional layer to extract a higher level of features from the output of pooling layers. So let's say we apply another convolutional layer with kernel size 5 by 5. And here we should use 20 different kernels. And then the result of this convolutional layer must be come with size 8 by 8. 8 is calculated from 12 minus 5 plus 1. That's 8. So 8 by 8. That is size for one feature map because we have 20 kernels. So the size of the convolutional layer output would be 8 by 8 by 20. And 20 is corresponding to the number of kernels used in this convolutional layer. And the total number of parameters in this second convolutional layer will be 5 by 5 and by 20. But these kernels are not 2D kernels. They are 3D. They come in 3D because it has a depth dimension matching with the depth of the input. And now the input is the output of pooling layer. So that is the feature maps with reduced size. It has 10 as the depth. So now this kernel should have the third dimension 10 matching with the depth of the reduced feature map. So we not only just have 5 by 5 number of parameters, we have 5 by 5 by 10 parameters for each kernel, and we have 20 kernels. And that is the total number of trainable parameters in this second convolutional layer. Okay?
Excuse me, Dr. Zhen, I might miss that. I was thinking how the pooling output is 12 by 12 and 10, the dimensions 10, and then the convolution output is 20. How it from 10 to 20? I understand
20 because we are using 20 kernels in this second convolutional layer. It is specified here.
Where? Okay.
Yeah. Just like this, we are using 10 filters in this layer. So the output is not this one. So the output must have 10 feature maps. And now we are using 20 kernels. So the output must have 20 feature maps. And for each feature map, the size is a 8 by 8 matrix.
So is it a number that we are just deciding or deciding?
Yes. this number of features is by our design. So we can use 20, 30, whatever numbers we specify.
Okay.
When should we?
Can I finish my one?
Oh, sorry. Yeah.
Yeah, right. So I understand 10, and then the second one will be 20 filters. And how these 20 stack into the 10?
Which 20?
Okay, 20 filters. I understand on the first 20 because the input feature map, input one, the really original input one is 1. Yeah, one access is vector, so it was 1D, and then after apply 10 filters. I understand the 10 filters are one by one. 10 layers of the filters apply to the input one by one, so it come to 10. Pulling output is 10. Am I clear? And then when the 20 of the apply
So,
to this one,
I
how
will
does
just
it apply? Yeah.
let's start from the pooling operations. So after the first convolutional layer, it is clear that there are 10 feature maps, right? And each come with size 24 by 24. So after the max pooling operation, the depth must not change, right? We should have 10 feature maps. Only the size or the width and height of each map should be reduced, right?
Yeah.
So now the output of the pooling layer must be 12 by 12 by 10. So there's no problem here, right?
No problem.
Okay. Now this 12 by 12 by 10 array will serve as the input to this convolutional layer 2. So now the input is a 3D array. So for 3D array as input, we are applying 2D convolution. So now, although we are specifying this kernel size as 5 by 5, it also suggests that it must have a third dimension matching with the size of the depth of the input. So that's why we have for each kernel, the kernel size must be 5 by 5 by 10. Is it okay now?
Okay.
So that is for one kernel, and we are going to use 20 kernel. So 20 kernel means 20 generated feature maps. So no matter if the input is 2D or 3D, if we are using 2D convolution, we will only have 2D. We will only generate one 2D feature map for each kernel. So
Got it.
we have 20 kernels, so we should have 20 2D feature map.
Yep. Thank you so much. I got it.
Okay. Other questions?
No?
Okay.
Thank you. That's answered. Thank you.
Okay, great. Okay. Then so after the convolution, just remember we still need to add the activation function on this convolutional result matrix. So we use ReLU to be applied on each entries in this feature map array. And then we would like to further reduce the data size by introduce another pooling layer. And here again, we use the max pooling of size 2 by 2. So it will just reduce the width and height of the input to its half. So now it will change from 8 by 8 by 20 to 4 by 4 by 20. So only the size of width and height are reduced, and the number of feature maps must be preserved. And then it's time to do as I said, we can treat this convolutional layer as some feature extractor. And so you can treat it as extracting different type of feature. So for this layer, it is extracting 10 type of different features. And for the second convolutional layer, it is extracting 20 higher level image features based on the combination of the 10 features in previous convolutional layer. And the pooling output is just used to reduce the number of feature values, because not all the feature values not all the values are meaningful or valuable. So we can assume that only the strongest signal is valuable in this feature map to represent each sub areas in the image. So we use pooling output to reduce the size of feature map to save some computational work. And so that's it. That's why how we organize the structure in this way. We extract the low-level feature, and then we preserve some useful information, and while reducing the size of the feature maps. And then we keep calculating some higher level of feature map based on the previous lower level feature map, and then we reduce the size of the feature map. And now what we have to know is some higher level feature maps or some stacked feature values, right? And then we can use these feature values to do the image-based task, like image classification task. So now we can use the neural network, the pure neural networks that is composed of neurons, layers of neurons, and the edges to do the work. We use the dense layers. So now these features are organized as 3D matrix. So to pass these values into the dense layers, we need to organize them as a column vector. So we flatten this 3D matrix into one column vector. So this is the process. So we flatten this 4x4 by 20 tensor into a column vector of 320 dimension for the column vector. And the number of entries in this tensor and the vector must be the same, because it is just a flattened version of the tensor. And then we use the fully connected layers to do the classifications. Normally we treat this part as classifier, and we treat previous convolutional layers and pooling layers as some feature extractor. So logically, we use convolutional layers to extract features, and then we use dense layers to do the classification task based on the extracted features from the convolutional layers. So fully connected layers are the normal feed-forward neural network layers. So these layers may have a nonlinear activation function or a softmax activation. Fully connected layers are last layers of the network after feature extraction has been performed by the convolutional and pooling layers. They are used to create final nonlinear combination of the features for the final prediction. So we have flattened the features into a column vector, and now we can keep stacking layer of neurons to combine these features, and then keep stacking more layers to further combine the features and do the, let's say, classification task. So in this example, we just first stack one layer of 100 neurons, and then stack another layer of 10 neurons. So we just keep stacking layers with fewer neurons so that it will preserve more important information. It's kind of doing such kind of feature selection and feature combinations in these different layers. And then lastly, we need to append the output layers. So let's say if we are doing multi-class classification task of 10 possible outcomes, let's say for handwritten digit recognition, we need to recognize if the input image is a digit of 5 or 0. So there are in total 10 possibilities, right, from 0 to 9. So we need to have 10 neurons in the output layers to represent the logits for each prediction for each class. And we also apply the softmax function to convert these logits into probability distributions, just like what we talked about in last week. Now we have go through the entire structure for a typical CNN model used for multi-class classification task. Then here's a question, like how many trainable parameters are there in this entire model? So let's first figure out where these trainable parameters reside. So there must be some trainable parameters in the first convolutional layer. It is held in this convolutional kernels, and also in the second convolutional layers residing in this kernels. And also there are some trainable parameters in the dense layers or fully connected layers, because there are some like edges, right, used to connect between dense layers, and the weight of this edge need to be trained. And these are also another set of trainable parameters. So in this case, for the first convolutional layers, how many parameters? We have 5 by 5, that is the parameter numbers for each kernel, and 10, that is the total kernels numbers we used in this convolutional layer 1. And another set is for the convolutional layer 2, what we have is for the size of the kernel we used, it should have 5 by 5, but it also has a depth dimension to match with the input, because the input is the output of pooling layer, and it has 10 feature maps. So we need 10 as the size of the depth dimension. So therefore, for each kernel, the size must be 5 by 5 by 10. And this would be the parameter numbers for each kernel. And we have 20 kernels in this second convolutional layer. And there is no trainable parameters in pooling layers, so we don't calculate those parameters. And then to calculate the parameters in the fully connected layers, so recall that we have flattened this 3D feature maps into a column vector. So in total, it has 4 by 4, that is 16 times 20. That in total would be 320 feature values. And we need 1 neuron to hold 1 feature value. So in total, there are 320 neurons in the input layer of this fully connected layers. And this input layer is connected to a fully connected layer of 100 neurons. So the edge number between these two layers must be 320 multiply the 100. So the trainable parameters between these two layers must be 32,000. And then we append another fully connected layer of 10 neurons to this layer of 100 neurons. And the edge between these two layers, must be 100 multiplied 10, and in total there are 1,000 layers. So the total number of parameters in this model, entire structure would be 250 plus 5,000 plus 32,000 and plus the 1,000. So that is the total trainable parameters in this model. Okay. And just notice that the previous calculation is not counting the intercept. So if we count the intercept, so one kernel come with one additional bias or intercept parameter. So if we have 10 kernel, so that means we need to plus 10. And for this layer, because we use 20 kernel, so we need to plus 20 bias. And for this, for the edges between the fully connected layers, we need to have, let's say, a linear combination that would be plus 100, and there would be plus 10. The bias number should be the same as the later neurons number, because each neuron is a linear combination between the weight and all the neurons in previous layers, and each linear combination must come with one additional intercept or bias parameter. So how many neurons in the later layer would require the same number of bias or intercept parameters. So if we count the intercept, we need to add some extra parameters in the model. Okay. Just a recap for the CNN structure. So why we use convolutional layer? So we stack this convolutional layers to extract different level of features. Let's say the closer the layers to the input image, the lower the level of feature we extracted. So for the first few convolution layer, it is just extracting the edge information or the color distribution in the input image. And later on, for later convolutional layer, it will combine these low-level features to generate some higher-level feature. We can see that it can represent some kind of complicated shape or some shape pattern, like some corners here. And for even later, that is later convolutional layers close to the output, the level of feature will be very high, and it is more abstract and very hard for human to interpret what these features are representing. But this trained extracted features would be useful for specific for the task where the model was trained on. And why activation functions like ReLU? So we need the activation functions to introduce nonlinearity to the model. So without the activation functions, the model is simply a linear model, and it cannot capture the complicated nonlinear relationship between input and output. So why pooling? We need to reduce the shape of the features while preserving some important information in the feature map. So we have seen for convolutional for the hyperparameters in this CNN structure. there in the convolutional layers, we need to define what's the number of filters, like how many filters, different filters we're going to use, and what's the size of the each filter, or what's the size of the filter? Is it 3x3 or 5x5? So what's the stride? So should we, when we slide the filter, should we move it just one location every time, or should we just jump over, let's say, 2 locations or 3 locations every time? So we need to specify if we what's the size, what's the step size for the sliding. And zero padding. So zero padding was related to if we are going to add some padding zeros around the let me see, around the operation. So let's say, for example, for this case, why we want to add paddings is under some situations, we may expect the extracted feature map to come with to have same size as the input image. So without the zero padding, the size of the convolution result might be less than the input image. So what we can do is we can pad some zero values around the original input image. Let's say we append 2 rows, one at the top and one at the bottom, and we append we pad 2 columns, one at the left and one at the right, around the original image. And now if we apply the kernel to this padded image, we can place the kernel at this location. And if we just input the if we just calculate the size of the output, we can, after padding, the input will be 7 by 7, right? Because we have 2 extra rows and 2 extra columns. So 7 minus 3 plus 1, that is 5. And this 5 is equals to the size of the original input image. So when we want to preserve the size of the input image, if we want to have same size for the feature map and input image, we would use the zero padding. So we add some zero values around the original input image and then do the convolution. Get back. And for the pooling layers, we need to decide if we are going to use max pooling or average pooling, and the size of the pool size and the pool stride. For fully connected layer, we need to define what's the width of each layer, like how many neurons we want to use in certain layers. And there are many activation functions that we can choose from. We can use ReLU or sigmoid, and we use softmax as the output layer. And for loss function, we need to know if we are going to use the cross entropy for classification problem, or we are going to use L1 or L2 distance for regression task. And we can choose from many optimization algorithm, and each optimization algorithm has its own hyperparameters, like learning rate. So we can choose stochastic or gradient descent, or with momentum or Ada gradient. And for the initialization of the kernel weights or those weights in the model, we can use random initialization. We can choose it from a Gaussian distribution or choose it from a uniform distribution. Okay, I will leave this video for you. It will talk about some, it will explain the convolutional neural networks concept. help you out better understand this concept. And now we will talk about some tricks for training such CNN neural networks. And we have known how to use this accuracy against epochs or loss value against epochs graph to identify if there are any signs for overfitting or underfitting problems to help us make decision to do the decision to either like stop the training or refine the models. So we will also talk about how to, like, when we identify some overfitting problems, what actions that we can do to prevent them. Like we have seen to use some like regularization term like L1 or L2 norm to penalize the large values for weight parameters. And we will also see how to use the dropout layers or dropout operations to facilitate the training for the model. It is another trick, a regularization trick used specifically for neural networks. So let's look at this case. So we can plot the accuracy against the epochs, and we can observe that the validation accuracy is keep increasing, but the training accuracy is the training accuracy is keep increasing, but the validation accuracy is just stable after epoch 3. So it may suggest that the model is overfitting to the training data because it performed better and better in the training data, but this improvement on the training data cannot be reflected on the validation set. So it probably means that the trained model is overfitting to the training data. And if we can also plot the loss against epochs. So the training loss is keep decreasing. That is our expectation. We are optimize the trainable parameters so that it can achieve lower and lower loss. But if we validate the trained model on the validation set, we can see that after epochs, let's say 5, the validation loss become increasing. That would be a sign of overfitting because we are expecting that the loss on both and validation and training data would be keep decreasing together while we optimize the model parameters. This turning point would suggest that now the model is starting to overfit to the training data. So why this overfitting can occur, especially in this CNN model or neural networks, because in deep neural networks, there are a lot more trainable parameters than conventional models. And normally we don't have like the matching level of training sample numbers. For example, there may be like over 3 million parameters to be tuned in the deep neural networks, but we may only have like 2,000 training samples in hand to tune these parameters. So we have talked about it in this situation when the trainable parameter is way more than the training samples, it is prone to be overfitting. So the first trick to deal with this overfitting problem is using the dropout strategy. So what dropout do is in each iteration of training, so that means for this iteration of one forward pass and one backward propagation calculation, we randomly mask 50% of the neurons or any other percentage. So that means we make half of the neurons in this neural networks to be disabled. So the disabled neurons will not contribute to the calculation of forward path and backward propagations. So we just treat them as not belonging to the neural networks. And this is the training process. So in each iteration, we kind of trained a subset of the neurons in this the complete neural networks. So in each so at the end, we basically kind of tune different version of a smaller neural network that is using subset of neurons in the complete neural networks. And this is for the training process. And for the prediction process, we disable the dropout strategy. That means we just keep all the neurons in the neural networks connected, and then we use all the parameters to do the prediction. So this dropout strategy only apply to the training process. But let's see how we do this dropout process, how we disable this certain neurons. So for a batch of training samples, it's just assume we are working on a mini batch optimization. So we randomly choose 50% of neurons and then set the selected neurons to 0 and multiply the unselected neuron by 2. So let's say for these layers. So before we apply the dropout strategy, the contribution of these 4 neurons would be all equal. Let's say we have equal weight for their contribution, all equals to 1. After we disable the first and third neuron, now the weight of the first neuron output should be 0. So we just set the weight for this output to be 0 and keep the second one, and third one is 0, and the fourth one is 1. So by setting this weight to 0, we kind of disable these 2 neurons. Like we disconnect its output from the connection in this neural network. But there is a problem now. So we reduce the weight of first and third neurons. That will make the overall contribution of these layers to be half of before dropping out strategy, right? So we also want to preserve the overall contribution from this layer. So we need to increase the weight of the enabled neurons. So that's why we multiply the unselected neurons by 1 divided by 0.5. So this 0.5 is just 50% of neurons. That's the percentage we set to disable among all the neurons. So now it becomes 0.2, 0.2. And now the overall weight from this contributed from this layer would be same as before. Before dropout, we has in total like 4 weight for this layer, and after dropout, we can also preserve this in total 4 weight for this layer. So this is the dropout implementation, and we have done for 1 iteration, and for another iteration, we just set different set of neurons to be disabled, and then to do the training to calculate the forward path and update the parameters in the connected or the dropped out neural networks. And here is the process. or mathematical representation for that. So the input is a vector of 5 neurons, and we calculate the linear combination between the weight and the input vector, and the result is Z1. And that would be the result of linear combination, and we apply the ReLU function. So it calculates the maximum between 0 and the provided value. And x1 is the value after activation function. So that would be the output of the middle layer. And then after the layer, we add a dropout layer. This dropout layer has 4 neurons or 4 values corresponding to the number of neurons in the yellow layer. So each entry is either 0 or 2 because we randomly disable half of the neurons. So we need to increase the weight of the neurons that is enabled. And we apply this mask to the result of the output of the yellow layer by using the entry-wise multiplication. So it is just doing the element-wise multiplication. So let's say for x1, it may be a column vector saying 1.5, 2, 3, 10, and the m, that is the be, let's say 0, 1, 1, 0. So basically it is doing the element-wise multiplications. So the result must be, say, 1.5 multiply 0, 2 multiply 1, 3 multiply 1, and not 1. There should be 2. Be 2. And 10 multiply 0. And you can see that by applying this entry-wise multiplications and setting zeros in this mask, we can just filter out the output from disabled neurons. And then the output of this dropout layer will be passed to the next layer, and it keeps doing the linear combinations and then calculates the probability distribution. So why this dropout works? In training, dropout forces the network to make decisions based on part of the features. So it disables some neurons. That means the feature hold in these neurons will not be contributing to the prediction. So intuitively, that means it is using not all the features in the image. It is using part of the feature map to part of the image information to do the prediction. So it can intuitively, it can say update this iteration using only the top half of the image, or it may says in this iteration, I want you to update the trainable parameter with only the bottom half of the image, or it may just randomly pick some image data from the entire image, like only use half of the pixels to do the prediction and update the trainable parameters. So in this way, the model, because this is performed in the training process, so why the model can be overfitting is because the model is highly relying on the value of certain feature or certain image area information or certain neurons. So if we don't, with this dropout strategy introduced, we kind of prevent such heavy rely preference for the trained model. So instead of relying on specific features or image areas or certain neurons, the trained model will will rely on all the neurons and make sure all the neurons would provide some meaningful information for the prediction. So that is why this dropout strategy will work. So this dropout strategy is also treated as a regularization regularization method for training the model. And another trick is about data augmentations. So we have seen that one problem is we don't have that much training samples to matching with the large number of trainable parameters. And we can do some data augmentations. We can generate more training sample from existing data. So we can flip, rotate, crop, shift, or add some random noise to increase the variety of the training samples. Recall that one limitation of the convolutional operation is that the generated feature map is corresponding to the location of the objects in the image. So with this data augmentations, we kind of provide more feature maps that can cover such flip, rotation, or crop, shift of the objects in the image, so that we can get more comprehensive feature extracted from the model using the model. Okay, and here is an example of some common process. So for horizontal flips, we just basically swap the image along the x coordinates, and we can also do some random cropping. We just extract sub area of the image and then scale the sub areas back to the original size of the entire image. So in this way, we can generate many samples for training. And we can also adjust the contrast or brightness of the input image to generate more training samples. So to train convolutional neural networks for images, we'd better always use data augmentations. So it will give you more data for free. If a layer has too many parameters, we put a dropout layer before it, because a layer has too many parameters, it's prone to be overfitting. How can we avoid or deal with this overfitting is we are limiting the input to this layer. We change the input to this layers. We use different subset of the entire input to train these layers, so that the layers can capture or capture the patterns capture the variety of patterns in the input. So these dropout layers should be placed before a layer that has too many parameters. And another, I think that would be the last trick for training a deep neural network, is use pre-trained model. So it is hard to train a deep neural network from the very beginning. So because the number of parameters is huge, and the deep neural network has huge capacity. That means it has high level of freedom. So you may be tracked, the optimization may be tracked at different local optima. So that would be a challenge. And we have limited training samples to train the neural networks from the very beginning. So if we just train a very complicated neural network using the limited data and without much tricks, it will very easy to result in overfitting. So one solution for that is take advantage of some pre-trained model, and in those models, it already got some features, feature extractors and layers, parameters trained and fixed, so that those layers can serve as the functionalities that we are expecting and help, and we don't need to further tune those parameters in the layers, in the pre-trained layers. So those pre-trained model normally are trained in a very large scale data set like ImageNet. It has like 14 million images with 1,000 labels to do the multi-class classification task. So what we can do is we already know that let's say the top is the bottom of the model and the bottom dense layers are top of the model. I know it is a little bit confusing, but let's just use this term. So the bottom layers are low level. We can see that this is a VGG16 model. So it is a very popular networks trained on the for image classification task. And we can see that the layers it used are just what we have learned: 2D convolutional layers, max poolings, convolutional layer, max pooling, convolutional layers, and max pooling. So it just organizes convolutional layers and pooling operations into some building block or units. So the bottom layers or convolutional layers are used to extract some low-level features, and these features should be universally useful to deal with all, let's say, all image-based tasks, no matter it's for image classification or segmentation or whatever, or recognition task. So these low-level features could be shared. Feature extractor can be shared or reused by other tasks. And the top convolutional layers would be more related to high level features tailored specifically for the model, the task that the model was trained on. So what we can do is we can borrow the bottom layers and use them as the feature extractors, and we don't need to tune the parameters in these bottom layers, and we can replace the top convolutional layers and also the classifier, the dense layers, and tailor them for our specific task. But the best practice is we freeze only the bottom convolutional layers. We freeze this blue convolutional layers, and we can train the top convolutional layers and the classifier. But the best practice is we don't train the top convolutional layers and the dense layers together at the very beginning stage, because when we initialize the parameters in the dense layers with some random values, these random values will generate very large gradient, and it will destroy the usage of the previous features combinations. It will destroy the high level feature extractor. So the best practice is we also freeze the parameter in in this top convolutional layers, and we first train the classifier. We first train the dense layers for our own task, and then if the performance is not as good as we are expecting, we then slowly unlock the parameters in the top level convolutional layers, and then slow to perform the update for the parameters in these convolutional layers in a slow pace. So we don't want to introduce a huge change on these parameters. We just want to have like minor tuning for the high level feature generations. Okay. So that answers the questions here. So can we merge the step 4 and step 5 together? That is, train the top layers and fine-tune the top convolutional layers. So this is the top layer, and this is the top convolutional layers. Can we combine them together? The best practice is we better just first get the top layer we better first get the top layer trained. If the performance is not good, we then slowly begin to train the top convolutional layers. The convolutional layers are for feature extraction. So the first few low level, the bottom layers are used for extracting low level features like edge, shapes, and patterns. And they can be shared with other image-based tasks. For high-level features that may be tailored for specific image task when the pre-trained model was trained. So in this case, they're used for ImageNet dataset for multi-class classification tasks. So we can fine-tune the high-level features. I think of the high-level fully connected layers, that is this part, as a classifier. So it is going to learn how to combine the extracted high-level features to deal with our specific task. So the less trainable parameters, the less prone to be overfitting. So let's say if we freeze all these convolutional layers and only left the classifier to be trainable, we dramatically reduce the number of parameters to be trained during the training process. And these are some result comparison for using the pre-trained model. And another trick is to use the ensemble method. So we can use different subset of data to do the training, and thereby we will train different models, and we can then let each model to do the weighting for the same input data and to vote for the final prediction. So this is one type of ensemble method called bagging. So it is using different subsets of data to train different models and let different models to predict for the same input and vote for the overall prediction. So this will show the workflow for that. We do the random subsampling and train the same model structure by using subsample of the entire data samples. And then thereby we will get 3 different models, although they have the same structure, but they are different models, and each will have their own prediction for the same input, and we just let them vote for the final prediction for the same data. Another ensemble method is varying models. So we can train different models using the same data. So maybe we can try different structures for the neural networks. We may just use some random initializations because some models is sensitive to the initialization of the parameters, and it may be locked at different local optimum. And we can try different optimization algorithm, and it will also result in different models. And similarly, after we get different models, we can ask these models to do the prediction by itself, and then we summarize their each individual predictions to vote for the final prediction.
Doctors?
Yeah.
So a quick question on the bagging. So when you say like voting in both ways, it's like end of the day voting. Is it like we always pick, for example, first one, we pick models more than the number of classes we have, like model types more than the classes we have to have a majority? Because if it is less than that,
yes,
we could end up not having a majority.
We can just use the simple strategy, like the majority of the prediction would be the final prediction. Let's say the the Model 1 predict 1, the Model 2 predict 1, and Model 3 predict 0, then we will choose Model 1. We will
Choose
choose
one.
class 1. Yeah.
Yeah, and we always go for more model types.
Yes, it
Model
also
types
applies to
than
these
the
very
classes.
models.
Okay, yeah. So because
Yeah,
like
of
if you
course,
have three
like
classes,
look, of course, you can set some different strategy for these votings. Let's say weighted vote. Let's say you trust more on the Model 1, so this would weight. It should have double weight than the others. Double weight more than the others. You can set different weight for uh the vote strategy, just like uh the nearest neighbor problem. We can you can design your own voting strategy, but the basic version is just we choose the majority.
yeah. Thank you, Doctor.
Okay, so there are some because the neural network is sensitive to hyperparameters and sensitive to random initialization for the weight parameters. And the stochastic gradient descent may also affect the stable status of the trained neural networks. So all these factors will result in like different local optima. So that's why we need to use the ensemble method. It will help to reduce the variance of the prediction. Okay, that would be all for today, and I will just leave this video for you to watch it in your own time. So, any other questions?
Yes, can I ask a quick one? In the dropout,
Yeah.
after you delete certain neurons, why did you have to increase the weight of those remaining neurons? Doesn't that defeat the whole purpose of?
Because intuitively, let's say we intuitively the output of these layers need to be passed to the next layer. Let's say to make it simple, let's say we have 4 neurons connected to like 1 neuron in let's say in the output, and we need to use this output to calculate the loss because for one iteration, it involves one forward pass and one backward propagation, right? So if we just simply disable the first two, the magnitude of the loss would be much different because it doesn't receive input from 2 nodes. So that's why we want to increase the magnitude of the rest of the output in previous layers so that we can maintain similar level for the values hold in this neuron. Does it make sense?
So we want to keep the same kind of.
Let's say it is holding value 1, 2, 3, 4, and all the weight is 1, 1, 1, 1. And now the linear combination for this value would be 1 plus 2 plus 3 plus 4. And if we disable the first two, now the value passed to the next neuron will be only 3 plus 4, right? Because all this disabled and the value cannot be passed into the next neuron.
But I thought the whole purpose is to like disabling the neurons so that you have some kind of more sort of like a generalized, how to say, not
Yes, but this is more related to the implementation, and because it also involve forward pass and backward propagation. So it needs to maintain same level or like magnitude level for the value passed to the loss passed to the next layers. Otherwise, the loss value would be changed a lot between iterations.
Okay, so you want to find some kind of balance so that
Yes.
the output is not changed dramatically.
Yes.
Okay, thank you.
Doctor, quick question now on the the convolutional network where we calculate the number of parameters that we need to calculate. Why haven't we considered the bias in that one? Because we don't have bias, or like why did we didn't take the bias into the consideration?
So bias is optional. So when we build the model, we can choose to include it or not. So it is optional. So that's why there are two situations. The prime numbers, the total prime number with intercept or without intercept. So there are two different variations. So you can choose, like, if you would like to build a model with bias or without bias. It doesn't matter that much because it is already complex enough to do that.
Right. In the convolution networks, bias applied to each layer?
Yes, bias apply to each kernel. So basically what you do is, let me find the slides. So what it do is it is doing the inner product of the matrix and then plus one bias. So it is doing the linear element wise. It is doing the element wise multiplication and sum them together. So after summing them together, it need to add the bias value, and this will be the final result of operation convolution operation. So this bias is just one bias value for one kernel. So this bias is another trainable parameters to be tuned.
Thank you, Doctor. Thank you.
Okay, any other questions? All good? Okay, great. That will be all for today's lecture. So I will see you all on Friday lab session.
Thank you, Doctor.
Thank you.
Thank you.
Thanks.
Thank
Bye.
you.
Thank you very much.
Thank you.
Thank
Thank you, Doctor. Good night.
Good night.
Good night. Thank you.